A plane that looks like a whale flies through European skies. It doesn't carry passengers, it carries other planes. Wings 100 feet long, fuselage sections as tall as a house. This is the Airbus Beluga XL, Europe's biggest cargo plane. 112 tons of freight, a cargo hold 29 feet across. Inside, it can fit 2 Airbus A350 wings at once. Without the Beluga, Airbus production would stop in a week. Today, we'll see how this giant is born, from an aluminum sheet to the first roar of its turbines. The Beluga XL is a puzzle made from parts created at 5 points across Europe. The base, an Airbus A330. Its lower fuselage, wings and landing gear are assembled in Toulouse. But the nose section? That's made by Stelia at their plant in Mayotte, France. 40 feet long, 18 tons. Inside, the cockpit, avionics, hydraulics. All on a plug-and-fly principle. Panels from aluminum alloy 2024 with copper and magnesium are formed on presses capable of 1,300 tons of force. The frame is assembled from bulkheads and stringers, then the skin is riveted on top. 12,000 rivets, each about 1/6 of an inch in diameter for a single nose. The upper expanded fuselage, the heart of the Beluga, is produced by Premium Aerotech and De Hard. 3 sections, 2 side panels and a roof. 29 feet in diameter, nearly 6 feet wider than the previous Beluga. Sheet thickness ranges from 1/10 to 1/4 inch. Each panel is reinforced with 30 stringers. Bulkheads are placed every 20 inches. Everything's riveted and bolted with titanium bolts, torqued to 90 foot-pounds. The cargo door, an engineering marvel. Stelia Rochefort, France. 33 feet long, 26 feet high. Area nearly 1,500 square feet, like a basketball court standing vertical. Weight 3.1 tons. Frame made from titanium alloy, Ti6Al4V. Titanium handles the loads. 24 latches hold the door, 12 on each side. Each latch clamps down with 3 tons of force. The door opens with 4 hydraulic cylinders, piston diameter 4.7 inches, pressure 4,000 psi. 3 minutes to open, 4 to close. Inside the door, hundreds of yards of wiring and hydraulic lines. They shipped the door from Rochefort to Toulouse on a barge, the same one that carried A380 sections. By sea to Bordeaux, by river to Langon, then 125 miles by road. The tail section, modified by Spain's Aeronova in the Basque Country. The vertical stabilizer increases by 50%, from 33 to 50 square feet. The massive bloated fuselage creates serious drag. You need stability. They add vertical end plates to the horizontal stabilizer, plus 2 ventral fins under the tail. 5 vertical surfaces total instead of 1. Everything's made from composites, carbon fiber. Layers of carbon fabric soaked in epoxy resin, laid in a mold and into the autoclave. 360 degrees Fahrenheit, 100 pounds per square inch, 8 hours. The composite fin weighs 1,300 pounds instead of 2,000 aluminum. December 2016, Toulouse. Line L34, a hangar spanning 130,000 square feet. Final assembly of the first Beluga. Lower fuselage with wings from an A330 goes on the jig. From above, a 50-ton crane lowers the expanded upper fuselage. They mate the perimeter. Hundreds of bolted connections. They drill quarter-inch holes through both sections at once, tolerance plus or minus 0.04 of an inch. Bolts get torqued with computer-controlled wrenches. The joint sealed with polysulfide compound, Works from -76 to +250 Fahrenheit. They mount the nose section, tail, vertical stabilizer. 3 months of work. Meanwhile, the guts. 50 miles of wiring in bundles of 50 to 100. 2,000 feet of stainless hydraulic lines. Pressure 4,000 pounds per square inch. 12 fuel tanks. 37,000 gallons of kerosene. March 2018. Engine installation. 2 Rolls-Royce Trent 700s. Each one weighs 12.3 tons. Thrust, 320 kilonewtons. 72,000 pounds of force. Fan diameter, 9 feet. 24 composite blades with titanium leading edges. The engine mounts to the wing through a titanium pylon with 4 bolts, each 1.9 inches in diameter. Torque, 2,950 pound-feet. 37 connections to each engine. Fuel, electrical, hydraulic, pneumatic. April through June. Ground testing. 200,000 checkpoint inspections. Every sensor checked. Every actuator verified. Flight control checks. Elevators deflect 25 degrees up, 15 down. Ailerons, 25 up, 15 down. Laser sensors monitoring. Accuracy to within 0.5 degrees. July 19, 2018. Blagnac, Toulouse. First flight. Crew of 6. 150 sensors recording 200 parameters 1,000 times per second. Takeoff thrust 96%. Turbine exit temperature 2,700 degrees. Fuel burn 12 tons per hour, 120 knots, 222 kilometers per hour, nose wheel liftoff, 140 knots, main gear liftoff, climb rate 1,000 feet per minute, flight level 350, 35,000 feet, cruise speed 0.69 Mach, 466 miles per hour, 4 hours 20 minutes airborne, landing nominal. Next up, flight test program. 200 flights, 700 hours. Maximum weight with ballast, 51 tons. Single engine flight. Crosswind landing at 30 knots. -22 in Sweden, plus 113 in Spain. Everything works. November 13th, 2019. Type certificate. The Beluga cleared for flight. January 9th, 2020. First commercial flight. Toulouse, Bremen, Toulouse. Cargo, 2 A350 wings, each 105 feet long, 21,000 pounds. Before, 2 flights with the old Beluga. Now, 1. Loading 70 minutes. Wings roll in on a trolley along floor tracks. 24 tie-down points with straps. Flight 1 hour 40 minutes. In Bremen, they unload the wings, load A320 fuselage sections, fly to Toulouse. 3 to 4 flights a day, 6 days a week. 1,000 flights a year across 6 aircraft. Without the Beluga, Airbus wouldn't build a single plane. Wings made in Great Britain, tails in Spain, fuselages in Germany, final assembly in Toulouse and Hamburg. The Beluga, a flying assembly line. Europe's industrial artery. 1 billion euros program cost, 167 million per aircraft, 30 years of service, 60,000 flight hours. If this was interesting, hit like. Did you know about the Beluga? Write in the comments. Subscribe. Here we show you factories you never knew existed.
Picture the irony. A city built in the middle of one of the planet's largest deserts forced to import sand. Yeah, you heard that right. Dubai, surrounded by billions of tons of golden dunes, buys sand from overseas. I'm standing on the edge of the man-made Palm Jumeirah Island, and beneath my feet isn't Arabian desert sand, but carefully calibrated, washed and sorted material that arrived here from the ocean floor hundreds of miles away. The sun beats down so hard the air above the asphalt shimmers, and the Persian Gulf humidity turns every breath into a struggle. But right here, between luxury hotels and turquoise water, one of the Middle East's most massive industrial operations unfolds. Welcome to the Dubai Marine Aggregates Plant, where the ocean floor becomes paradise beaches. Dubai's problem is paradoxical and brutal at the same time. The desert sand surrounding this city on all sides is completely useless. Billions of years of wind have polished each grain to perfect roundness. Under a microscope, desert sand looks like glass marbles, smooth, polished, beautiful. But it's precisely this beauty that makes it unfit. Round grains don't bind to each other. Try building concrete from them, it'll crumble. Try creating a beach. It'll wash into the sea with the first wave. Desert sand is like trying to build a house out of glass marbles. Ahmed, the plant's chief engineer, explains to me, squinting in the sun. We need sand with sharp edges, angular, rough. We need marine sand. And that's why Dubai, sitting on an ocean of sand, sends giant dredges to the bottom of the Persian Gulf. Every year they pull up millions of cubic yards of seabed sand, which then goes through an incredibly complex processing operation. This isn't just extraction, this is surgery at the molecular level. We're boarding the dredge Al Muharraq, a floating factory 400 feet long. This isn't a ship, it's an industrial monster. I feel the vibration of massive diesels driving pumps that move 15,000 cubic meters per hour. A suction pipe 4 feet in diameter descends 80 feet down to ancient deposits of shell rock and coral sand. Captain Saleh, a man tanned almost black with wrinkles as deep as cracks in stone, points me to the echo sounder monitor. See that line? That's a layer of quality sand. For millions of years, the waves of the Persian Gulf crushed corals and shells. What wind did for the desert over billions of years, the sea did in millions, but the result is opposite. When the suction pipe touches bottom, the sound changes. Before it was the monotonous hum of the pumps, now there's a grinding added. Sharp fragments of shells and corals flying up through the pipe. A mixture of water and sand in a ratio of 1:5 rises to the surface. Here on the dredge deck, the first stage of processing begins. The pulp, that's what they call this dirty, murky mixture, feeds into the primary screen. It's a vibrating steel table the size of a tennis court, covered with a mesh that has quarter-inch holes. Here's where the big chunks get filtered out. Coral fragments, shells, sometimes even pieces of sunken ships. The fine fraction falls through and enters a cascade of washing drums. The water here is seawater, but it runs through a filtration system. 3 massive cylinders, each about 13 feet in diameter, rotate at 20 revolutions per minute. Inside them are spiral blades that churn the sand and water so intensely that every grain of sand gets mechanically cleaned. Salt, organics, silt, it all washes away. I watch as dark brown sludge comes out of the first drum, light gray from the second, and from the third, nearly clear water with clean sand at the bottom. The temperature inside the drums hits 113 degrees Fahrenheit because of friction. This isn't just washing, it's thermal disinfection. Any organic residue, bacteria, algae, they all die in this hot whirlpool. After washing, the sand moves to hydrocyclones. devices that separate material by density and size using centrifugal force. Picture giant metal cones 20 feet tall. The slurry gets pumped in at a pressure of 8 atmospheres. Inside the cone, it starts spinning at 300 revolutions per minute. Heavy particles, coarse sand, and small pebbles get pressed against the walls and sink down. Light particles, silt, clay, very fine sand, get carried upward by the rising water current and get dumped as waste. I walk up to the outlet of the lower stream. Coming out here is sand ranging from 0.02 to 0.05 millimeters, the perfect size for beach sand. If the particles are smaller, they turn to dust and blow away in the wind. If they're larger, walking barefoot on that sand is uncomfortable. It cuts your skin. Ahmed grabs a handful of wet sand and holds it out to me. It's heavy, dense, and every grain has an irregular angular shape. Feel those sharp edges? That's coral and shells. They lock together. Waves can't wash this sand away. It creates a stable surface. The next step is desalination. Even after 3 wash cycles, sea salt remains in the sand. If you don't remove it, within a few months the beach will be covered in a white film, and any nearby metal structures will start rusting twice as fast. The sand goes into long troughs where it's flooded with pressurized fresh water. It's expensive. Every 1,000 cubic meters of sand requires 200 cubic meters of desalinated water. But in Dubai, water is valued more than oil, and the plant has its own reverse osmosis desalination unit. The process takes 4 hours. The sand slowly moves through a trough about 500 feet long, while pressurized fresh water, at 3 atmospheres, pours down from above. The salt washes out, concentration drops from 35 grams per liter to 0.5. The plant's lab constantly takes samples. They're not just checking salt, but pH levels, heavy metals, organic contaminants. The standards are strict. This sand is going to touch the skin of thousands of tourists. Kids will be crawling on it. One mistake and the beach's reputation collapses. Now for the really interesting part, color and texture calibration. Natural Persian Gulf sea sand has a grayish-white tint. It's beautiful but not postcard perfect. Tourists want to see golden, warm, almost caramel-colored sand, like in the Maldives or Thailand. And this is where the alchemy begins. In a specialized facility, the sand is mixed with mineral additives. This isn't paint. These are crushed natural minerals. Iron oxide gives a reddish tint. Dolomite flour, creamy. Quartz dust, a golden shimmer. The proportions are calculated by computer based on samples of perfect beach sand from around the world. Engineers loaded into the database photographs and physical samples of sand from Bora Bora, the Seychelles, Zanzibar. The program analyzes color temperature, brightness, saturation, and produces a recipe. For Palm Jumeirah, the recipe is this: 92% base sea sand, 5% dolomite, 2% crushed yellow quartz, 1% iron oxide. Mixing happens in drum mixers with a volume of around 1,750 cubic feet. The drum rotates for 20 minutes, ensuring absolutely even distribution of the pigments. The final stage is heat treatment and stabilization. The sand is dried in rotary kilns at 250 degrees Fahrenheit. This kills off the last bacterial and fungal spores and activates the mineral bonds between the additives and the grains. The color gets baked in and becomes UV resistant. After the kiln, the sand is cooled and treated with a silicone-based hydrophobic compound. It's a thin, invisible layer that makes the grains slightly water repellent. Why? So the sand dries faster after rain or waves, doesn't turn muddy, and doesn't form puddles. This is Dubai Marine Aggregates know-how: self-cleaning sand. The finished product gets loaded into dump trucks and shipped to the beaches. But that's not the end of the story. Every beach has a monitoring system in place. Sensors buried at different depths measure moisture, temperature, sand displacement. If a storm starts washing away the surface, they truck in a fresh batch right away. Twice a year, all the sand gets sifted by special machines, removing trash, seaweed, shell fragments. It's a living system that requires constant care. I'm standing on Jumeirah Beach watching a wave roll onto the shore and retreat, leaving behind a perfectly smooth, slightly damp surface of golden sand. Beneath my feet, a pleasant coolness. The sand has already dried since the last wave. No clumps, no mud, no sharp shells. Each grain of sand has traveled from the ocean floor through washing, sorting, dyeing, and heat treatment. This isn't nature. This is an industrial symphony where technology creates the illusion of pristine wilderness. In Dubai, even the sand is a high-tech product. A city in the desert that imports sand from the ocean floor, processes it in factories worth billions of dollars, and creates beaches that look more natural than nature itself. This is Dubai, a place where reality surpasses imagination, and human ingenuity defeats the laws of geography. If you found it interesting to learn how Dubai's perfect beaches are created, give this video a like. Write in the comments what beaches around the world you visited and which sands seem the best to you. And subscribe to the channel to keep discovering the amazing technologies hidden behind the everyday things in our world. Every year, dozens of nuclear submarines get retired around the world. Steel giants weighing over 10,000 tons. Inside each one sits a reactor pumping out hundreds of megawatts. But what happens when their service ends? How do you cut out the heart of a nuclear monster and survive a battle with invisible radiation that lasts for months? Temperatures here hit 14,000 degrees Fahrenheit. A mistake isn't measured in seconds, it's measured in centuries. In this video, you'll see the decommissioning process from the first cut to the last ton of melted metal, and find out what becomes of a submarine giant's armor. The process begins with the most dangerous stage, removing the spent nuclear fuel. The submarine is moved into a special enclosed dock. Around it, a real scientific laboratory unfolds. This is a battle against invisible radiation. It doesn't last days, it lasts months. Inside the reactor core are fuel assemblies. They've kept this monster alive for decades. Each assembly is a bundle of thin zirconium tubes, about half an inch in diameter. Inside, uranium dioxide pellets. One assembly is 13 feet long. Weight, 660 pounds. The reactor holds 100 to 120 of them. They're removed using remote manipulators. Each assembly emits a lethal dose of radiation, 500 roentgens per hour at 3 feet. That'll kill a person in an hour. The assembly is lifted by a crane rated for 20 tons and lowered into a lead container. Container wall thickness, 10 inches of pure lead. Container weight, 17,000 pounds. Only lead stops gamma radiation. The containers are loaded into special rail cars with water cooling and shipped to temporary storage. This stage takes 3 to 4 months of continuous work. If you're interested in seeing how things built for war get taken apart, subscribe to the channel. Here we show you production processes hidden from view. Once the fuel's extracted, it's time for the reactor compartment. This is a massive section of the sub. Weight, 1,500 tons. Length, 33 feet. Diameter, 30 feet. Engineers don't dismantle the reactor piece by piece. Too dangerous. The metal itself is radioactive. Neutron flux from the operating reactor bombarded the steel for years. Iron atoms transformed into radioactive isotopes, so they cut out the entire compartment whole. They use oxyacetylene torches. Flame temperature 5,800 degrees Fahrenheit. Mix of acetylene and oxygen. Feed pressure 217 pounds per square inch. The torch burns through 3-inch thick steel in 10 minutes. They cut in a ring around the compartment. 2 cuts, forward and aft. You get a cylinder. All technological openings are welded shut with half-inch steel plates. Welding, electric arc, 1/4-inch diameter electrodes. Current, 350 amps. You get a sealed capsule. It's lifted by a 200-ton crane and loaded onto a barge. The barge is towed to a burial site. In Russia, that's Novaya Zemlya. In the US, Hanford site. There, the capsules are placed in concrete trenches 65 feet deep, covered with earth on top. They'll sit there 300 years until radiation levels drop to background. Decontamination is the longest phase. The reactor compartment's cut out and shipped off, but the work's just beginning. Decades of coolant circulation left their mark. Thousands of feet of primary loop piping, pumps, heat exchangers, steam generators, all of it contaminated. Radioactive isotopes soaked into the metal. That's induced radiation. Teams in protective suits scan every foot, hunting for hotspots, areas with elevated readings. They use DP5B dosimeters. Sensitivity, 0.01 milliroentgen per hour. Every pipe gets checked, every pump, every valve. Then chemical flushing begins. They run acid solutions through the primary loop piping. Sulfuric acid at 10% concentration. Temperature 140 degrees Fahrenheit. Pressure 115 psi. The acid dissolves the oxide film off pipe walls. Radioactive isotopes go with it. Solution gets collected in 13,000-gallon tanks, filtered through ion exchange resins. Radionuclides precipitate onto the resin. Resin gets incinerated at 2200 degrees Fahrenheit. You get ash. Mix the ash with cement and pour it into concrete containers. That's Class 2 radioactive waste. Chemistry doesn't work everywhere. Valves, gate valves, filters, they dismantle those by hand. Teams of 3. Shifts last 30 minutes. Can't go longer, the dose accumulates. Every part gets packed in a lead box. Box weighs 265 pounds. Walls, 4 inches of lead. If contamination levels run too high, they encase the part in concrete right inside the hull. Special attention goes to the reactor's biological shield. Massive plates of lead and polyethylene. Lead layer, 6 inches thick. Polyethylene, 12 inches. Lead stops gamma rays. Polyethylene slows neutrons. Weight per plate, 4 tons. 8 plates total. They pull each one with a crane. Decontaminate with ultrasound. Frequency, 40 kilohertz. Power, 3 kilowatts. Ultrasound breaks down the oxide film. Then they rinse the plate with alkaline solution and dry it with hot air at 250 degrees. Only after thousands of air samples and surface swabs, when everything reads 0, they open the dock to regular workers. Now it's not a nuclear facility, it's just a complex steel structure. Cutting the hull. After decontamination, the submarine is ready for final dismantling. The submarine's hull isn't ordinary metal, it's an alloy built for war. It withstands water pressure at depths of 1,000 to 1,300 feet. That's 30 to 40 atmospheres. Hull thickness, 3 to 4 inches. A K29 grade steel. Tensile strength, 100,000 pounds per square inch. Regular cutters won't touch it. They use plasma torches. Plasma is ionized gas. An electric arc creates the temperature. Voltage, 300 volts. Current, 400 amps. Power, 120 kilowatts. Argon gets blown through a nozzle 1/8 inch across. Pressure, 90 pounds per square inch. Flow rate, 1 cubic foot per minute. The arc heats the argon to 15,000 degrees Fahrenheit. That's 1.5 times hotter than the surface of the sun. The plasma jet shoots from the nozzle at 670 miles per hour. That's the speed of sound. Under that stream, 4-inch thick steel melts in 5 seconds. The torch follows the marked line. Cutting speed, 8 inches per minute. Sparks and smoke fly from the torch. Flame height, 10 feet. Spark temperature, 1800 degrees. The second tool, oxygen lances, a 10-foot steel pipe, 1-inch diameter. Inside, a bundle of steel rods, each about a sixth of an inch thick. Pure oxygen flows through the pipe at 150 psi. Flow rate, 50 cubic feet per minute. The rods are ignited with an acetylene torch. They start burning in the oxygen. Steel burns. Massive amounts of heat pour out. Temperature in the burn zone, 6,900 degrees Fahrenheit. The lance burns clean through the steel, leaves a molten seam 2 inches wide, burn through speed, 20 inches per minute, faster than plasma. But it takes serious skill. You guide the lance dead perpendicular, deviate more than 10 degrees and the burn's incomplete. Crews of 4. Protective suits made of Kevlar, masks with number 13 filters. They block infrared and ultraviolet radiation. Without the mask, your retina burns in 1 second. They cut from bow and stern, working gradually toward the center. The hull gets cut into cylindrical sections, each section 20 feet long, 30 feet in diameter. Weight, 400 tons. Cranes rated for 800 tons lift the sections and stack them in the sorting zone. Metal sorting. Every hull fragment gets checked again with dosimeters. They're hunting for isotope traces in microcracks and weld seams. If the device clicks, the fragment gets isolated, sent for recleaning or special disposal. Only clean metal receives a safety certificate. It can leave the shipyard territory, then sorting by chemical composition. Steel grades HY80 and HY100. These are high-strength steels. Nickel content, 8%. Chromium, 2%. Molybdenum, 1%. These alloying elements are treasure for metallurgists. Nickel provides toughness. Chromium, corrosion resistance. Molybdenum, strength at high temperatures. Regular hull steel. AK-29 gets sent for remelting separately. Titanium parts, the sail, fairings, also separate. Titanium doesn't melt with steel. Different melting points. Titanium, 3,034 degrees Fahrenheit. Steel, 2,795. Copper alloys, wiring, heat exchangers, to non-ferrous metal. Aluminum alloys, bulkheads, ladders, to aluminum scrap. Reborn in fire. High-strength steel heads to the metallurgical plant, loaded into an electric arc furnace. Capacity, 100 tons. 3 graphite electrodes, 24 inches in diameter. 600 volts, 60,000 amps. 36 megawatts of raw power. An arc ignites between the electrodes and metal. The arc zone hits 6,300 degrees Fahrenheit. Metal melts, becomes a liquid lake. The melt reaches 3,000 degrees. Melting time, 3 hours. Lab techs pull samples every 30 minutes. Analyze composition on a spectrometer. Adjust with ferroalloy additives. Precision matters. Carbon tolerance, plus or minus 0.05%. Nickel, plus or minus 0.1%. Finished melt pours into a ladle. The ladle weighs 200 tons. From the ladle, it flows into molds. Create slabs, steel plates. 6.5 feet by 20 feet. 10 inches thick. 23 tons each. Slabs get rolled into sheets or cut into rebar stock. Yesterday's warship armor plating becomes a river bridge support or a skyscraper skeleton. Steel that once withstood depth charges now holds up bridges. Metal doesn't die. It lives again. If you found this fascinating, hit that like button. Drop a comment. Did you know submarines get recycled for 300 years? Subscribe. We show you how the old dies and the new is born.